So, complex numbers are actually a special case of, oops, that's a TE. Complex numbers are a special case of vectors. In fact, they are specifically a special case of two-dimensional real vectors, which is neat. So, a complex number, a plus bi. You guys have all seen these before?
Yeah.
Maybe? So, these work essentially the same way real numbers do, except what? What is the one addition that I've made to the real number system in order to create the complex numbers?
I.
Yeah. We made I, and really the only thing is I squared is -1. Otherwise, these may as well be regular real numbers. The actually kind of cool thing is that by may as well regular real numbers be, that sentence got all out of order. Although these may be the regular real numbers with this extra I, it turns out that this actually creates a bunch of interesting structure. So, we could take a number a plus bi and think about it as a vector AB in R2 as a vector space. This funky little hat just means I'm thinking about this thing as a vector space. You guys cool with that? As opposed to I'm thinking about this thing as a geometric space. Does that distinction make sense? I really should go back over here and put one there. That's with me? So, if I think about, say, taking a real number like k and multiplying it by a complex number a plus bi, my brain says, oh, well, in regular real number land, I would just kind of distribute this through. You guys see that? If I just kind of distribute that through, I get ka plus kbi. You guys see how that's just scalar multiplication? Okay, cool. That's a good start. Does a plus bi added to c plus di work like vector addition?
Yes.
Yeah, I mean, if I was doing real number stuff, I'd be like, well, that's a plus c plus b plus d, and we could factor an I out of the b plus d. Right? Or bi plus di, rather. And I would see that this is a vector kind of like a plus c, comma, b plus d, which is really the same thing, right? What's the piece of structure I gain from this?
What do you mean by piece of structure?
There's one more thing I could do with complex numbers that wouldn't make sense with vectors. So the complex numbers are not just the two-dimensional real vector space. They actually have one more piece of structure. So I could formulate the dot product, right? That would be useful. That would tell me about the angles between complex numbers, which is something that we'll talk about a lot. But there's one more thing I gain, and I'm going to tease you with it today because it's never going to happen again.
Are you talking about, you're still talking in 2D world?
Yep. So the complex numbers have one more operation that's not listed on that board. And I have to do this to highlight that there's something you don't get with vectors. So you can add vectors, right? You can scalar multiply. So when you take a scalar and a vector, scalar multiply, you get a vector, right? When you take two vectors and add them, you get a new vector. When you take two vectors and dot product them, you get a scalar. Is that how I expect multiplication to work?
No.
Not really. Usually you multiply two numbers, you get another number.
Yeah.
Right? You don't like multiply two numbers and then get an object in your living room. Like it doesn't switch categories. But when I do the dot product, it switches categories, right? It goes from pair of vectors produces number. Like that feels weird.
Alright, talking about division.
Kind of.
Like,
Could you,
So I'm talking about multiplication.
like, squaring them, you could, like, if you squared it, you could get rid of the eyes, kind of.
That's a half decent idea. It won't get rid of the eyes because the outside and inside terms will still have eyes in them when you FOIL. But the fact that I can even square them is new. Right? I don't have vector multiplication over there because in general vector multiplication isn't defined.
yeah.
You guys with me on that? So the complex numbers are a special case of the two-dimensional real vectors in that they have a new operation that does not generally exist, vector multiplication. So I can take a plus bi and multiply it by c plus di. This is something that we won't see with vectors generally. Vectors generally don't have multiplication. It's not something that's usually defined. Even better, the complex numbers have division. Some vector spaces have multiplication defined. There are few and far between with division defined. In fact, there's basically one. This one. That's a little bit of a lie. We'll go into it some more later. But there are like 5 options, and this is the only one that works the way you'd want it to. So, we could multiply. We would multiply by foiling, right? So I'd get AC minus BD, right? That's these guys and these guys. And then I'm going to get plus, and my outside term is going to be AD, my inside is going to be plus BC, and that'll all have an I on it. You guys with me on that? Okay, part of defining this today, like part of the reason I want to dwell on C today, is that if you're in differential equations, this will happen a lot in there. So I want you to see the overlap between these two subjects. If you're not in differential equations, you get to see this now, because I promise it'll be useful when you take differential equations. These guys also kind of, a thing adjacent to these guys makes computer graphics work. Like 3-dimensional rotation, the way we're going to do it in this class, is really cumbersome to compute. It just takes too long. It would make games really slow. So there's a thing that's a little bit related to the complex numbers that speeds it up, and we'll get there. Yes. Yeah, quaternion rotation is the thing. The last thing here is that you could define A plus BI divided by C plus DI. Division would work. You guys all believe that? Okay, cool. That's what I want you to have for complex numbers for right now. We'll do more with this as we go on. Don't get attached to the idea of multiplying vectors together. This is demonstrated as an exception, not because it is something you will see often. Good to go?